Hello again. This is the Pencrest High School AP Physics C video series. This is video 5B, Rotational Dynamics. So effectively, what we're going to be talking about here is the application of Newton's laws to objects that are rotating. So the ones we're most familiar with, Newton's first law and Newton's second law. So we're going to talk about the rotational analogies for these. Newton's first law says that the sum of the forces equals zero. For rotational motion, Newton's first law says the sum of the torque equals zero. More importantly, the second law, sigma F equals ma for linear motion, and for rotational motion, sigma torque equals I times alpha. So we're going to need to talk about torque and rotational inertia in this video. So torque is the tendency for an object to want to rotate due to the application of a force some distance from the rotation axis. Where the force is applied and its direction is just as important as the force's magnitude in terms of the torque that it generates. Torque has units of Newton meters. It would not be appropriate in any case to use joules for torque, even though Newton meters is comparable to joules when we are measuring energy. Now, the generic formula for the torque generated by a force is torque equals Rf sine theta. R is the distance from the rotation axis to the location where the force is applied. F is the force itself, and theta is the angle between the force and R, effectively. If we don't know that, you might recognize that one vector times another vector times the sine of the angle between them, you might recognize that as a cross product. So on your formula sheet for Physics C, torque is indicated this way, where R is the vector position of the force with respect to the rotation axis, and then F is the force. Both of these are vectors, which indicates that they could be indicated to you in IJK notation. Typically, the object and the forces on it are sort of oriented in the plane of the page, which means that the torque terms would be sort of out of the page in the positive z direction or into the page in the negative z direction, using the standard sign convention. The sign convention that works for rotational kinematics variables, position, velocity, acceleration, also goes for torque. It's also common for the orientation of the object, or at least the R from the rotation axis to the location where the force is applied, for these to be at right angles, in which case the torque reduces to R times F, because the angle between them would be 90. Now, when we consider the vector nature of a torque term, we can think about what this would look like and how it would be reported in a three-dimensional environment. So when we look at this situation here, you can see where the x and y and z axes are. We want to consider this force that is exerted at this location P. The point P has a negative x, a negative y, and a positive z components for its location. The force is oriented in the positive y direction, so it's up. And we want to consider the torque that this force generates with respect to the origin along each of the axes. In other words, this force will generate an x component for its torque, a y component for its torque, and a z component for its torque. We want to take the straight right hand and point the fingers in the direction of the force. So we are pointing our right hand straight up. And then we want to curl our fingers in such a way so as to grab each axis one at a time. So you want to curl your fingers in such a way that you would grab, for example, the x-axis. So if my hand is pointing straight up, I'm going to reach curl my fingers into the screen in order to grab the x-axis. And my thumb will point in the direction of the torque about that axis. So when I reach back, I reach into the screen and grab the x-axis, my thumb points to the left, which would indicate that in the x direction, this force generates a negative torque in the x direction. In the z direction, I would have to sort of twist my hand away from me to the right and then curl my fingers to the right in order to grab the z-axis, and my thumb would be pointing into the screen in the negative z direction. Now, of course, we can't grab the y-axis because it is parallel, so there's no way I can curl my fingers in such a way as to go around the y-axis. So this force in particular would not generate any torque in the y direction. It would have an x and a z component, but no y component. So here's another one. You can try it. Once again, you want to orient your right hand so your fingers are pointing to the left, and you want to try to move your hand in such a way as to grab each of the axes. We would find that since it's parallel to the x-axis, it generates no torque there. The y component of the torque is negative, it points down, and the z component is negative, it points into the screen. So now we want to talk a little bit about rotational inertia. This is the tendency for an object to resist being rotated, the same way that mass resists being accelerated in a linear sense. The rotational inertia includes the mass of the object, but how that mass is distributed relative to a particular rotation axis is more important. The farther away mass is distributed from a rotation axis, the harder it is to make that object rotate. And that would indicate a higher or larger rotational inertia. It has a symbol capital I, and it is not a vector. It's measured in kilogram meters squared. The meter squared indicates that sort of how far away that mass is distributed is sort of more important than the mass itself. Now we've looked at systems of particles. So we know what a particle is. A particle has no physical dimensions of its own, but it can be oriented in some way relative to a rotation axis. So if we have a particle or a series of particles, and we want to know what its rotational inertia is with respect to a particular axis, all we need to do is take the mass of that particle and multiply by r squared, where r is the distance, perpendicular distance from the rotation axis. More often, we're going to be considering the rotational inertia of a solid rotating object that does have physical dimensions, like disks or rods or balls, hollow and solid, hoops and wheels. These objects can rotate around a fixed axis, and their masses are distributed in such a way that their rotational inertias can be reduced to a relatively simple formula. The formulas come about through the application of calculus. We can assume that the objects we have will be uniform and homogeneous, so their density does not vary. They will be regular, consistent geometric shapes, and the mass is evenly and consistently distributed across the object. In that case, we have a table of sort of values here that we can use. Typically on the AP exam, the rotational inertia of a particular shape will be provided for you. In the event that you need it, I will be able to provide that for you. So again, more often than not, we're dealing about hoops, discs like this one, cylinder, a thin shell, a hoop. These are the kinds of things that we're going to be running across more often than not. So now these formulas that you see in the table, they assume that the rotation axis goes through the center of mass of the solid object. We're going to need to consider situations in which it does not. So if it doesn't, we need what's called the parallel axis theorem. I here is the rotational inertia about the actual rotation axis. I sub Cm is the rotational inertia about an axis through the center of mass, which we would get from the table. M is the mass of the object, and h here is the distance from the center of mass to the actual rotation axis. So for example, if we had a disk with a rotation axis that was tangent to its edge, like we see here, applying the parallel axis theorem, I equals the 1/2 mr squared is the rotational inertia of a disk when the rotation axis goes through the center of mass. And then plus mh squared, we can see that the axis is located here on the edge. So it is a distance r from the center of mass. So there's the mr squared term. And when we add those up, we find that the rotational inertia here is 3/2 mr squared. Could get considerably trickier when you have a composite solid object like this one. In this case, what we would need to do is to find the rotational inertia of the rod by itself about an axis that is not through the center of mass, but at the edge of the rod. So we would find from the table that I sub Cm is 1/12 ml squared, and then plus mh squared, the h for the rod would be L over 2, because the rod's center of mass is in its middle. We would then need to find the rotational inertia of the ball about an axis that is not through the center of mass. If the ball were solid, it would be 2/5 mr squared, and then plus mh squared, h for the ball would be L plus r, because that's how far its center of mass is from the rotation axis. We would need each of those individual components and then add them all up to find the rotational inertia of this composite object. So we'll see that more than once. Okay, so there's a lot here. And next up is rotational angular work and rotational kinetic energy. So until then, enjoy, and I'll see you again soon.